with that, we are right at 9 o'clock, and we have this morning basically a review of all the undergraduate inorganic chemistry that we think you need for the week in 2.5 hours. So it'll be a bit of a high-speed review, and we're going to spend the first hour on group theory. And just for me to have a bit better idea of your backgrounds, how many of you had group theory in your coursework already? Okay, a lot of you, but certainly not all of you. And those of you who've had group theory in your coursework, how many of you are comfortable applying it to spectroscopy? Okay, a smaller number. Okay, no, that's fine. I mean, I think this for me just gives you an idea. I will be very clear, I can't do justice to group theory in 1 hour, but I will do my best to give you an idea of its importance and the power of group theory. And for me, this is something I really quite enjoy teaching because honestly, for me, group theory is the reason I'm a chemist and a spectroscopist. I think so many people will tell you they're inorganic chemists because they fell in love with colors. And although I appreciate that aspect of it, for me, learning about group theory and really being able to visualize something that you could express mathematically and then actually predict the behavior of a molecule was pretty amazing. And I think that more broadly speaking, group theory, of course, is based on symmetry. And symmetry is a concept that for us, I think, as human beings, just simply resonates so strongly. And that's, of course, because symmetry is something we see everywhere in nature. I obviously just took a lot of nice photos I found from the internet, hopefully none with any copyright infringement issues. We'll just have to leave that out of the online filming there, Hoberg, if I do. But of course, it's not just that we see it in nature. Human beings, we mimic symmetry in almost every field and in a huge range of human-made objects. And so I picked some very famous examples of symmetry on this slide, some less famous. But of course, I think everyone knows pretty well Da Vinci's Mona Lisa and the fact that for 500 years, we've discussed this photo or this painting in terms of symmetry, right? And that the beauty of it is in its symmetry and its deviation from symmetry that makes it all the more human. And this is, of course, also a concept that evolutionary biologists study. This is something intrinsic in our selection of mates. It's something that graphical artists use in order to impart power and clarity to their messages. And of course, it's something that we see in everything from architecture to integrated circuits. But more broadly speaking, in all of the fields that use symmetry, chemistry included, we do this in order to bring order to complexity. And so for those of you who've already had group theory, when you look at these molecules, you most likely not only see all of their symmetry, but for many of you, you're immediately assigning a point group. And for those of you who don't immediately see that, we'll get you there this week. And of course, I think for an icosahedron, that's very clear, but maybe for elemental sulfur on the left, that takes a bit more time. And you won't immediately identify all of this, but it's important to just sort of appreciate these concepts and how we use it. Because in a sense, these give us incredible predictive tools. And I would like to say, in a world of AI, where computers can do more and more, there's incredible power and satisfaction in still being able to do this yourself and to work out something with pen and paper and make a prediction. And that's something that we want you to do. We want you to not just use ORCA as a code, but to come to it as informed, educated spectroscopists and chemists and ask questions that are based on your own understanding and intuition. And so that's one of the big goals of this school. And so let's start a little bit with just why we use group theory in chemistry. And I was told to try not to move too much, but I need to move a little bit since we're also being filmed. And I famously don't stand still during my talks. But we're going to start with just why we actually use group theory in chemistry. And of course, as many of you know, for orbitals to interact, they have to have the same symmetry. So assigning symmetry is a really important concept when we start to talk about bonding interactions. And of course, group theory is the way that we actually do this. And it gives us qualitative insights into bonding. So for instance, ligand field theory that we're going to talk about after the coffee break, which dictates the splitting of the d orbitals. Molecular orbital theory, the forming of bonding, non-bonding, and anti-bonding orbitals. This is so important to concepts like bond order that ultimately dictate things like reactivity. And of course, in the context of this school, a particularly important use of spectroscopy of group theory is in spectroscopy, really to determine allowed and forbidden transitions. That's something that you're going to do a lot this week, and to determine the symmetry of normal modes. And so you'll do that this afternoon in the vibrational spectroscopy practical. And so this is kind of why we're taking a little bit of time to review these concepts, even for those of you who've already had it, just so it's all sort of fresh in your memory and at your fingertips to use in the practicals. And so this is basically, as I already said, but just a basic understanding of group theory as it applies to chemical bonding and spectroscopy is what really helps you develop your chemical intuition, and I would argue also makes for better computational chemistry questions. This is really a background that will be a lens through which you ask questions and that you ask, hopefully, good questions. Okay, so we're going to start with basically just symmetry operations and elements and how we go about actually defining eventually point groups and character tables. And so a symmetry operation is something that transforms an object into a configuration indistinguishable from the original, right? And we're going to go through what each of those symmetry operations actually is. The symmetry element is the point, line, or plane around which that operation has defined. And so we have 5 symmetry elements that we want to talk about: identity, point, line, plane, and line plus plane. Maybe just for my information, how many of you in the audience are crystallographers? Do we have any crystallographers out there? A few, okay. We'll bring you in with your notation a little bit later, but for now we're going to use the notation of molecular chemists, and later I'll also bridge to some of the crystallographers in the room. So basically, let's start with the identity element. And this is the easiest one, and I'm always going to basically define these within a coordinate system. So every object, of course, has the identity element. This is fundamental in group theory, and that means for every point, x, y, z, when I operate the identity element on it, I get back x, y, z. I do nothing. So that's probably the easiest one to understand and the one that by definition must always be there. And the next we have is point elements. And this is specifically inversion, or I, where you basically take a point, x, y, z, and send every point to minus itself, to minus x, minus y, minus z. And I'm showing here just 2 examples of molecules that clearly have inversion symmetry. And so for most of you, the octahedron is the clearest example. It's one to keep in mind because we use this a lot in spectroscopy as an example of something that has inversion. And that presence or absence of inversion has huge consequences in terms of spectroscopic selection rules. Okay, and then here is another example that has inversion, and that of course only occurs when this molecule is actually staggered, so that the green chloride comes through the center and comes out completely to minus itself, similarly with the other 2 atoms. Okay, our next symmetry element is the line, or what we refer to as C sub n in group theory, which is an n-fold proper axis of rotation. And this is when you rotate by 2 pi over n. So for instance, if it is a C4 axis, then it's 360 over 4, or a 90-degree rotation. And a good example of something that has C4 symmetry is a square, right? There is an axis on which I can rotate that and return the same square. And so I'm just showing that here in very clear terms, where we can imagine a square where I label the corners as 1, 2, 3, 4, and a single C4 axis would be one clockwise rotation, which moves 1 to 2, 2 to 3, and 4 to 1, as pictured here, right? And so you can just think of that in terms, again, of the transformation of the coordinates, where x, y, z goes into minus y, x, and z. And so what you always want to do is to identify the largest Cn axis in your molecule. But it's important to remember, right, that a C4 axis is made up of multiple C4s, right? Because I can rotate by 90 degrees and return the same thing, or by 180 degrees, which is a C4 twice, which is classified also as a C2, or I can do a C4 3 times. When I do a C4 4 times, or a full 360 degree rotation, that is now, of course, the equivalent of the identity. And these are just formalized mathematical classifications that we need to be aware of in order to eventually construct our character tables. Okay, and so the next symmetry element is a plane, or a mirror plane, which we denote as sigma or as a sigma hat. And so here, for instance, if I have a coordinate x, y, z, and I put my plane in the my mirror plane in the xz plane, of course, nothing happens to x or z. I return the same exact coordinates, but I send y into minus itself, right? And so that's what the plane operation actually does. And these planes are generally defined with respect to the highest order rotational axis, right? And so if I had that planar square, for instance, I would have a C4 axis and a plane perpendicular to that. That would be a sigma h when it's perpendicular to the highest order Cn axis. It's a sigma v when it's parallel. So we think of this as a vertical plane parallel to the highest order rotation and a horizontal plane perpendicular to the highest order rotation. And of course, just as with any other symmetry operation, when I repeat that operation to its completion, it must always return the identity, right? It always takes it back on the nuclear axis to something that is indistinguishable from itself. Okay, so let's just quickly go through some of these examples. These are the mirror planes and the rotational axis in ammonia. So here you can see the C3 threefold axis. And I'm actually drawing on that actually one of the planes that actually is a sigma V plane from that. And so you can see that in principle, there would be 3 sigma V's that run through each of the NH bonds. And you can see also that there is no plane perpendicular to that. There is no sigma H because the ammonia actually is bent out of the plane, right? And this would be in contrast to something like boron trihydride, where everything sits in a plane. And so I have not only those 3 sigma V's, but the added symmetry element of actually having a horizontal plane of symmetry. Okay. The last symmetry element is what is known as an improper axis of rotation, and this basically is 2 symmetry elements, both a line and a plane. And I'll show you why in just a moment, why we have to define this element together and not as 2 separate symmetry elements. But the way this works, for instance, is if I have an S4 axis, then I do a C4 combined with a sigma H. And so what happens here is that my C4 axis, of course, now switches the ordering of y and x, taking x into minus y, y into x, just as we did before. And because I'm rotating along z, z is unchanged. And now if I do a sigma h with an xy, that means my xy positions of minus y and x are unchanged, but I take z into minus itself. And there are 2 types of improper axes of rotation. One is when Cn and sigma h exist independently, and the other is when neither the Cn or sigma h axis exists independently in the context of the nuclear framework. Okay? And so here are the kind of 2 extreme examples of that. And it basically is a general rule that whenever the Sn is actually odd, then the Cn and sigma h exist independently. And so this is an example that you can very easily see in eclipsed ferrocene. This is something that, for those of you who know your point groups already, would immediately look at and say it's D5H, right? And you can see that because it is eclipsed, that every carbon is above the other carbon, when I rotate it by 1/5 of a rotation, everything actually overlays each other. And because it's fully eclipsed, a sigma H plane actually also exists through the center of the molecule. And so what happens when ferrocene is actually staggered? And most of you who've had this before would already guess, of course, that what happens is I lose my independent C5 axis, and I also lose my independent sigma H. And so what's actually happening here is that I do have an Sn axis, but it actually is, in this case, an S10, right? And so for Sn even, there's always a collinear Cn over 2 axis, or a C5. And so these are general rules that come out of whether it is an even or odd improper axis of rotation. Okay, so we can and do basically take the time in molecules to identify all of these symmetry elements and then assign point groups. I think for most of you who've been doing this a long time, you sort of look at a molecule, assign a point group, and don't take the time to actually identify every single element anymore. But this is just kind of a reminder of how we do that. And in molecular symmetry, we use normally the Schoenflies symbols. These are the symbols that combine all the symmetry operations into mathematically defined groups that have a specific order we define as H. And then we organize them into the character tables. Now for the crystallographers in the room, I just wanted to make the notation that these Schoenflies symbols are what is generally used for molecules and spectroscopy. Crystallographers will be more familiar with the Hermann-Maugen symbols. These are generally, of course, used for crystal symmetries, and they include the point group symmetries as well as translational symmetry. And so today we're not talking about any translational symmetry, but I will, in these little beige call-out boxes, for those of you who prefer this notation, give the notation that crystallographers would be used to. What I want to point out, though, and the reason I didn't introduce the symmetry elements in both notations, is because there are, and this is just a table of the equivalencies between the two systems, there are equivalencies in some cases, but they're not always defined the same way. So for instance, a plane of reflection in the Hermann-Maugen notation is an M, but there's no distinction between the vertical, horizontal, or sigma D planes that we'll talk about later, the dihedrals. And so this is why for us from a molecular perspective, we think about it somewhat differently, although there are certainly strong equivalencies. Okay, so as I already said, what we're going to do is combine all the symmetry operations into a mathematically defined group. And we can start with one example and ask the question, what are the symmetry elements that are present in this molecule?
Identity.
Identity, yeah. Anyone see anything else? No, right? So this is just the single order H and a C1 point group. Okay, so let's do another one. This is planar, so you'll already tell me that identity is there. What else is there?
Mirror plane.
Exactly, yep. And what do we label that? That's going to be a sigma H in this case. And so this is the CS point group. And these low symmetry point groups tend to be the ones that we look for first, just when we're kind of trying to see something that has very little symmetry elements. Okay, what about this one? What symmetry do we see here? Yeah? Anything else? It's planar? So you also have a sigma H because it's planar. And this is also a case where you also have a improper axis of rotation, in part because you have the C3 that you identified, and since everything lays in this plane, when we do the sigma H, it also returns the same thing. And so this would be what we define as a C3H point group, or more generically, a CNH. And that's the Hermann-Malgan notation for those who prefer that. And so what we would do is also, in terms of determining the order, we would see that we have the identity. We have a C3 twice, sigma H, S3, and S3 twice, and that gives us an order of 6 for the point group. And we'll talk about later why this is important in terms of looking at character tables. Okay, and so we can go back to ammonia, which we already did together before. So we identified already that it had a C3 axis and it had 3 sigma V's. And again, just emphasizing that sigma V is when we're actually parallel to the principal axis, sigma H when it's perpendicular. And I haven't introduced sigma D yet, but this becomes more important for other higher symmetry groups, where you have it parallel to the principal axis but bisecting fewer atoms. And generically speaking, that's something you clearly see in an octahedral. And so I won't go through all of these examples, but this is just all of the symmetry elements in an octahedron. I actually, sorry, for some reason I have animations that I didn't expect to be here. I'm basically marking here where all the C4, C3, sigma H, sigma D axes, you can see the sigma D there isn't bisecting the equatorial atoms, and that's why it's a dihedral as opposed to the sigma V that bisects more. But this is something, again, in 1 hour, we don't have time to go through all of it. But if you're not familiar with this, or if it's something that you don't immediately see, these symmetry elements, I put the QR code and also the website for the symmetry at Otterbein. They have a symmetry challenge. So it's, I don't know, late at night, bored, something you want to do. This is actually a really nice website for visualizing symmetry elements. And this is something that, as I said, eventually one sort of stops doing. You can see that this is a group for octahedral of order 48. So you don't normally pick up your octahedral molecule and try to figure out all 48 elements. You just stop doing it, right? You look at it and you see an octahedron. And this becomes even more true once you get to really high symmetry groups, right? I mean, for an icosahedron, you have an order of 120, right? And although you can sit there and try to identify it, most of the time it's something that we very quickly identify and simply assign and then use that. Okay, so let's go ahead and just go quickly through the flowchart. So for most of you, when you were taught this, you probably were taught this using these flowcharts until you absolutely saw everything and didn't need the flowchart anymore. But in general, we start by either identifying something as very high symmetry. So typical examples, especially relevant to this week, are tetrahedral and octahedral. I, as an X-ray spectroscopist, will use these examples like crazy because we're talking about examples that have centrosymmetry or have inversion versus examples that don't. And this dictates a lot of properties in optical spectroscopy and many, many excited state spectroscopies. So this is an important one for us. And then sort of our next grouping would be to readily identify these symmetry groups where you actually have an infinite order. And these are, generally speaking, the linear systems where either you have inversion, like you do in CO2, and you end up with a D infinity H, or in this example, like HCN, you have an infinite rotation axis because it's linear. You can rotate it any small infinitesimal amount, and it always returns the same molecule. And this we assign as C infinity V. So if you don't have a very high symmetry axis, or you don't have a particular low symmetry group, then, sorry, we basically already did this. These are the low symmetry groups we already assigned together, so that would be your next option. But then the next thing you actually would do is ask the question if there are any axes of rotation. And so as I said before, anytime you look at a molecule, what you're always looking for is the highest order axis of rotation. And one thing I do want to emphasize, and I'll talk about this more in my ligand field talk, is symmetry doesn't have to be rigorously high symmetry to use the benefits of group theory in spectroscopy. So a lot of times we're talking about approximate symmetry. So just keep that in mind and use these rules somewhat in a relaxed way when you think about things. Because obviously in real world molecules, they're not normally looking as high symmetry as what we teach in group theory. But I would identify then this highest order rotation axis and ask if there are any perpendicular C2s, right? And so here, if I have this planar D4H molecule, I can see I have a fourfold axis of rotation, but clearly perpendicular to that, there are C2 axes. And so this broadly actually defines the D group of molecules, that it has perpendicular C2 axes. Okay, after this then, if the answer is no, we're looking at either C groups or S2N groups outside of the higher symmetry D groups. And so for instance, this is an example of C4V, and you can see because I've replaced this axial CO with a chloride, I've actually lost my perpendicular twofold axis of rotation. And I have a high order C4, and this C2 is actually along the same axis as the C4, right? So I have a C4 once, a C4 three times, and then the C2 that is the 180. I have two sigma Vs and the sigma Ds that bisect through the atoms. Okay, and so again, there are many, many forms of this table. This is obviously a pretty old school one, probably from my own graduate or undergraduate work, but there are more modern versions of this, and again, you can find it online in various forms. But the reality is what we want to get to are actually generating these character tables. And so in order to do this, we actually organize all of the symmetry operations into these character tables, where basically we have every symmetry element in the top row, and then we have below that these irreducible representations that contain the complete mathematical definitions needed to define that group. And so let's talk a little bit about what's happening in this character table. And so the important thing, everything we've been talking about, when we talk about symmetry, we say, well, with a given symmetry operation, the nuclear framework turns into itself. But that isn't actually true with what I'm going to refer to as chemical objects. So you heard these aren't observables yesterday, and that's true, but you're going to have to bear with me because we're still interested in talking about them. And things like orbitals, if you think about them and you want to use them, you can use them in the context of group theory, but what one has to understand is that the orbitals themselves will have different transformations under these symmetry operations. And that's actually how we're kind of constructing these irreps. And importantly, for your vibrational spectroscopy symposium, these irreducible representations actually correspond to normal modes. They correspond to what is or isn't allowed in different kinds of vibrational spectroscopy like IR and Raman. And so basically our irreps are the way we actually systematically characterize these chemical objects. And if you see a 1 here, it means that whatever that chemical object is, or whatever my coordinate is, that it goes into itself with that given symmetry operation, so it stays the same, or it goes into minus itself, meaning it doesn't stay the same, right? And so I personally always find this easiest to do with p orbitals as a start. That's something that chemists, we have a clear picture of how the p orbital is going to look like at the center of our molecule. And so what you can kind of intuitively see is if I take water, which has a C2V point group, and I look at the character table, so let's just pretend I looked this up in cotton, I would see that if I actually do a C2 axis of rotation, the PZ orbital goes into itself. If I do a reflection in the YZ or bisecting in the XZ plane, the PZ orbital always goes into itself. So it transforms as one under every symmetry operation, and that's exactly why a Z actually appears here in the character table. This is how PZ transforms in the C2V point group. In contrast, if I look at what happens with PY, what I actually then see is that if I do a C2 rotation, it goes into minus itself. And if I do a sigma V in the XZ direction, so perpendicular, it would go into minus itself, whereas if I took it within the plane of the board, it would go into itself. And so the PY orbital, I would say, goes as -1, -1, 1 under C2V, and it transforms hence as Y. So that's where these actually come from. And this is, in a sense, how we're going to later relate it to actually build up our molecular orbital diagrams. Okay, so some just important nomenclature. The order for group H is the number of symmetry operations. And so in this case, I would actually have the identity once, a C2 once, because a C2 twice is E, it doesn't count again. I have 1 sigma V and 1 sigma V in the YZ plane, so it has an order of 4. And we arrange these actually in classes, so each one of these is a class. So we have 4 classes, and each class gives us 1 column in the table, right? And this has important constraints because the number of classes equals the number of irreducible representations. So if we have 4 classes of operations, there are going to be these 4 operators. There'll always be 4 irreducible representations. So this will always be an n by n matrix, right? So if you want to generate your own character table, that is how you know this, right? You could sit down, identify all of the symmetry elements, and then generate your character table. And so if you actually look at this, you always have E, the identity, and the identity actually has to transform, as you know, into itself under every irrep. And the sum of the squares of the dimensions has to equal the order. So this is just a way to check that the character table is correct. Obviously, if you're using online character tables or Cotton, you're not thinking about this all the time, but this is just a reminder mathematically the conditions this character table needs to actually fulfill. And another important part is that for any irreducible representation, the sum of the squares multiplied by the number of operations in the class has to equal the order. And so here I'm just showing that example where we take the sum of the squares, and for each and every case, that actually has to return the order, which is 4 in this case, as we already said for C2V. And another important aspect, and what actually makes it kind of easy to work this out, is that the irreducible representations themselves have to be orthogonal to each other. So if we take A1 times A2, this needs to equal 0, and that's what we're just showing here, just as a check. And then finally, a totally symmetric representation, so something that transforms into itself under every symmetry operation, has to appear in every character table. Okay, so let's just spend a little bit of time looking at the matrix representation of these symmetry elements, because that's in fact where these character tables come from, that each operator that we defined can be described as a matrix. And it can be described as a matrix that operates on the XYZ coordinates. So for instance, and we already actually showed this at the very beginning, although we did it a bit more intuitively, if I have a C2 along Z, what I see is that Z goes into itself, but because I rotate 180 degrees, X goes into minus itself and Y goes into minus itself. So this is my C2Z matrix that I operate on my coordinate, and I can get out then minus X minus Y minus Z. And then I can then express these coordinates independently. So this actually forms then the XYZ basis set for the C2 operator in C2V symmetry. This allows me to actually fill out part of my character table without ever having to look it up in the Cotton textbook, right? And then I can do the same thing with the identity. This is a very easy one to write out because everything goes into itself, so it's a diagonal of 1, 1, 1. where everything returns 1, 1, 1. And then I could also do the same with my reflection planes, right? And so if I have, again, my x, y, z coordinates, I have a plane in the xz, that means x and z are unchanged, but y goes into minus itself. Then my matrix operating is 1, minus 1, 1, and that returns x minus y, z. And this becomes then how I report in the column under sigma v how x, y, and z transform. So these are parts of the columns that are starting to build up the full content of every irreducible representation. And we could then do the same thing with a sigma v in the yz direction. And there, of course, y and z stay the same, but x goes into minus itself. And so what we do is we replace these complex transformations, which some of you can do really well in your head, and other people struggle with this more. It's just the nature of it. But we can basically replace it with very simple matrix multiplication. And so this makes life quite a bit easier. And so what we can do is, without ever having to look up a character table, we can actually say that for C2V, I've basically figured out how each of these operators transforms in the x, y, and z coordinate. But what you'll see is we did say we have 4 columns, and that means there needs to be 4 irreducible representations. And so it means I'm missing 1 irreducible representation, and this is a case where one can easily solve by inspection, knowing that my 4th irreducible representation needs to be orthogonal to the other ones that are present, right? And so this is how I actually complete my C2V character tables. You can also do this mathematically, and I'll show those expressions later. But what I want to actually show you is we've solved it by inspection, and we can also assign our irreps by basically just looking at how they transform under different operators. And so anything that transforms under C2 as 1, so if it's symmetric to a C2, it will be A. And then the 1 or minus 1 is just the symmetry with respect to the first axis of reflection. So if it's positive, this is A1. If it's negative, it's A2. Whereas B means it's negative with respect to the primary Cn axis. And again, the 1 and 2 is the symmetry with respect to the first mirror plane that you're listing. This is also why sometimes you have to pay attention to people's conventions, because you'll sometimes see B1s and B2s flipped depending on how people have chosen their coordinate system as well. Okay, so let's look at this. What we already saw before and discussed before is how these orbitals transform under each operation. So we basically talked about the fact that x, y, and z transform as our px, py, and pz orbitals. But what we didn't assign is A2. So what is the actual orbital that transforms as A2 in this symmetry? What orbital would actually have a symmetry with respect to a rotation around the z-axis, but be anti-symmetric with a reflection with respect to xz or yz? Yeah.
Isn't it the d orbital that's in between the two axes?
Exactly, exactly. So it would be the xy that actually fulfills that. And so that's why when you actually see these completed character tables, I didn't actually draw it here, you would have an xy transformation on that axis. And I guess the other important point I wanted to make is that these transformations that we show in the character table, this isn't just how the pxyz orbitals transform, but these irreps, they correspond to dipole allowed transitions, right? The dipole operator transforms as x, y, and z. And so when you get to your vibrational spectroscopy, that is where this is actually coming from. And any mode that is x, y, or z active can actually be dipole allowed, right? And so here I'm just showing in C2V symmetry that you have symmetric modes for water that transform as A1, as well as asymmetric modes that transform as B2, and both of these are actually different types of dipole allowed vibrations that Maurice is going to go through with you guys in more detail. Okay, so here's finally that completed character table in the C2V point group. What I did want to point out is that the Raman active modes are the ones that result in a change in molecular polarizability. So these are all the binary products are the ones that we're talking about with Raman. And for IR active, we're talking about the XYZ, right? And so what we do see is that in C2V symmetry, there are both IR and Raman active modes. But it's important to keep in mind that group theory tells us what's possible. It doesn't necessarily tell you that you see it, right? And this is always also an interesting caveat. It's just mathematically possible. In reality, we normally only see 3 Raman active bands. Okay, let's take an example that's maybe a bit more real and closer to the way you might actually use this in your own work or when you're reading the literature to decide whether or not a mode might be IR or Raman active. And so I'm going to take an example from Jay Groh's group at Princeton. That's a bit of an old example, but it's a nice example of the first manganese 5 transdioxo complex. And so it's kind of fun to now use this for something that was published in JACS and ask the simple question, can I, just by looking at this, predict what the IR and Raman active modes are going to be? And you know, obviously the giveaway is they have both Raman and IR, so you know at least that this works. And so let's just take a look at that. And we already discussed the fact that IR requires, of course, a change in dipole. And so if I was interested in the dioxo, for instance, to have a change in dipole, I would need some sort of anti-symmetric mode. Whereas to have a change in polarizability for the Raman, I would need to have some sort of expansion. Both oxos would need to move out, right? That would be my change in polarizability. And then I can actually do something really simple and just ask myself, okay, if I think about the symmetry of this, right? It's D4H, right? I have those nice perpendicular C2s that we talked about relative to the principal C4 axis that runs through my manganese transdioxo. And if I look at this mode, this symmetric breathing mode, if I do a C4 rotation on it, it stays symmetric. And if I do a sigma H, it stays symmetric. But here what I see, this mode visually, if I contract and I actually elongate, I'm still positive with respect to a C4 rotation. But now because one oxo got longer and one got shorter, I become negative with respect to the sigma H. And so I can make a prediction about the modes and basically then check myself in a character table. And what I can see, for instance, is if I have the requirement, which we saw in our Raman active mode, that I'm positive with respect to a C4 and positive with respect to a sigma H, there are only 2 irreps that follow that. And in fact, only one of those irreps that is actually Raman active in terms of a change of polarizability. So this would already mean I could just look at a molecule and say that's my A1G mode, which is quite helpful, right? And then what I can also do then is take the same rules that we had for our IR modes, and there we saw that we were symmetric with respect to C4, but anti-symmetric with respect to the perpendicular plane of reflection. And so when I look at this, I again see there are only 2 irreps, A1U and A2U, that could actually satisfy that, and only one of those corresponds to something that transforms as a dipole allowed transition, right? And so then I basically can say that A2U is my IR active mode, right? And so this just is a good way to get intuition. Now, the reality is that sometimes you can do simple inspection, but sometimes the molecules are a bit more complex, and then we need to actually use group theory to assign things. So let's take this molecule where I have a hydride and 5 bound COs. And the first thing I want to figure out is actually how many IR active modes I actually have and how many Raman active modes I have. And for most of us, this is going to be hard to do by simple inspection. And so what we instead need to do is to assign the point group, generate the reducible representations that correspond to these 5 COs, reduce that representation into its irreps within the assigned point group. And so that's what we're going to just do briefly now together. Okay, so here is our molecule now. And what we want to determine is under every symmetry operation, what happens to those CO ligands, right? They don't sit at the center of the point group, they're at the periphery. And so I actually have to see what happens to them at each operation. And so here it's always easiest to see the identity operation, because if I operate the identity on all 5 of these COs, every CO returns itself. And so under the identity, the value is 5 for the reducible representation. Now, if I do a C4 along the z-axis, this is my z-axis, what happens, I rotate this 90 degrees, so this goes into here, this goes into here. So everything in the equatorial plane switches when I rotate 90 degrees, but this axial CO goes into itself. And the same thing happens with a C2. Now, if I do a sigma V, recall the sigma V actually bisects the most atoms, and it is parallel to the principal axis of rotation, or to the C4. You can see that all of these COs, 3 of them, would go into themselves. So I have a value of 3 in my reducible representation. And then when I get to the actual sigma D, that's going to actually bisect between them. And so only 1 CO will actually go into itself. And so this is actually now the representation I need to actually reduce. Okay? And so there is a sort of formula for this reduction. And so this A sub I is the number of times a given irreducible representation appears in a reducible rep. And so the formula breaks down as 1 over the order of the point group times the coefficient for each symmetry element. And so by that I mean 1 for E, 2 for C4, 1 for C2, 2 for sigma V, and 2 for sigma D. Don't forget these. These are like the #1 mistake that undergrads make on their exams, right? They leave that part out and then get the wrong irrep. And then you have the character of the reducible representation times the character of the irreducible representation. And so what we do then is mathematically, to work this out, we have a order in the group of 8, so that came from summing this here. So it's 2, 4, 6, 7, 8 is the order of my group. And then I basically just plug in this formula. And I get a total of 16 over 8, or 2 A1s that appear in this irreducible representation. And I don't want to bore you by like going through every single arithmetic exercise. You guys have all of this uploaded on the cloud. You can look at it later if you need to. Check my math. But basically what we see is that when we break this down, it is composed of 2 A1s, 1 B1, and an E. And now we can then ask the question, which of these are IR active? And if you want, you can derive the character table yourself. Practically speaking, most people are going to just pull it out of Cotton or online, right? But when we look at this, then we can see that the modes that transform as X, Y, or Z, these are our IR active modes, and the Raman active modes are A1, B1, and E that I boxed in blue, right? So this just gives you a way to actually really determine that, and to also just make informed decisions about what you expect to see, right? And sometimes this is a really important question, especially if you're doing synthetic chemistry and you're trying to characterize your molecule, that you are proactively thinking about which is the right method to use. What mode am I actually expecting to see, right? Okay, so with that, let's just summarize what we've been through this morning. The symmetry of a molecule, as we already discussed, is defined by the symmetry elements that render a molecule indistinguishable from itself. And these molecules are organized into point group. Every point group has the same symmetry elements, operations as other molecules within the same point group, right? So this is why once you learn these, you start to have intuition about, oh, my molecule's tetrahedral, I know how it behaves. My molecule's octahedral, I know how it behaves. And the character tables, of course, they allow us to define the point groups in terms of its irreducible representations. And these are mathematical constructs that we can directly relate to the chemical objects that we care about and want to discuss, concepts like orbitals and vibrational modes and allowed and forbidden transitions. And that's basically what I'm summarizing here. So with that, I wanted to make a few recommendations that if you're new to symmetry in chemistry, it's a lot of fun. And I actually, if you're completely new to it, this is one of the books that I always recommended to my undergraduates or to people who are new to this. This is the kind of book that you could read on a plane and like get through all of the introductory to symmetry elements and operations. A slightly more advanced text is the Carter text, which goes a little bit further. And I think for many people, the text they've had is Cotton. It's an incredibly polarizing text. I like it. Other people say, take the character tables out the back and throw the textbook out. So that's actually Frank. But so it is a matter of personal taste, I think. But I mean, mostly what we'd like to do is get you excited about the fact that even these simple and seemingly old concepts, they still are modern and they still have predictive power. And we want you to do your computations with this in mind. And so many of you have learned this already, and we're just sort of encouraging you to dust off what you learned and see how it's relevant to what you're doing today. And then maybe just one last comment for the crystallographers. This is also another primer for point and space groups. So for those of you who want to move towards crystallography and are interested in the full translational symmetry of the crystal, which also gets really fun if you want to do things like single crystal spectroscopy, then you want to delve past point groups and into the space groups. And with that, I will close by thanking you for your attention and also the online sources that I stole images from, and thank you for your attention.